Now we're going to look at this situation where we don't know the population standard deviations. And this is more realistic because if I don't know the population means, I probably don't know the population standard deviations. But if I have samples, then I can know S1 and S2, the sample standard deviations. But this is a situation where we actually need to break this up into two cases. So before, when I didn't know sigma and I only knew S, we said our test statistic should be a T. That's still true here. If I only know my sample standard deviations, my test statistic is going to be a T, but it turns out that I'll have two kind of subcases to figure out exactly what formulas I should use. So the first case is that the variances, the population variances, are not equal. And in that case, our test statistic looks pretty similar to our test statistic when we did know the population standard deviations, and we just replace our sigmas with s's. So we have the square root of s1 squared plus s2 squared, s1 squared over n1 plus s2 squared over n2, all under the square root. And in this case, this is our test statistic, and in the notes on the left, you can see this really big formula for degrees of freedom toward the bottom here. And so we would use this test statistic and that degrees of freedom. And I know this looks kind of intimidating. And so in this class, if you have a situation like this on a quiz or an exam, I'll go ahead and give you the degrees of freedom because I know this can be a lot to calculate and looks a little bit messy. And the other case is that our variances, our population variances, are equal. So sigma 1 squared equals sigma 2 squared. And in this case, you can see in the notes that our test statistic, it's still a T, and in the numerator, we still have the same thing in the numerator. But in the denominator, we'll have something different. So our standard error is a bit different here. It's the square root of SP squared, and SP squared is something we call the pooled variance, times 1 over n squared, or n1 plus 1 over n2. And that pooled variance is this weighted average of our sample variances. So this is n1 minus 1 times s1 squared plus n2 minus 1 s2 squared all over n1 minus 1 plus n2 minus 1. And this denominator, you might notice, looks kind of like the sum of degrees of freedom that we've dealt with in the past. And in this case, this is the degrees of freedom. So the degrees of freedom is n1 minus 1 plus n2 minus 1, which ends up being, if we combine these, n1 plus n2 minus 2. So the degrees of freedom is a lot easier to deal with in this case. But this is the case where we have to find our pooled variance and find our test statistic a little bit differently. But something that might be bothering you is this is all in this situation where we do not know the population standard deviations. And then I told you that our test statistic depends on whether our population variances are equal or not equal. That might seem weird. If I don't know the sigmas, how do I find out if these sigmas are equal or the sigma squareds are equal or not equal? That might seem kind of weird. But if we think back to something we've done before, we have figured out, or we have seen, how we do a hypothesis test to figure out if two variances are, if we can show that they are not equal. So if we should assume they're equal, or if we have enough to say they're not equal based on the sample. And we saw before that the way we would do this is using an F test. Our test statistic would be an F, and we would look at this ratio of sample variances. And so we know how to test to see if we should assume that our variances are equal or not equal. to know which of these cases we are in. And this might start seeming like a lot of work because we kind of have these nested things that we're testing. We're kind of doing this overall hypothesis test where we're comparing two means, and within that we need to do an F-test to kind of figure out which case we're in. That probably feels like a lot. And so in this class, in homework or quizzes or exams, you might have to separately do an F-test, but when you're doing one of these hypothesis tests to compare two means, in this case where we have independent samples and only know our S's and not our sigmas, I will tell you, or the homework will tell you, if you should assume that the variances are equal or not equal. And that helps you know which case you're in and which formulas you need to use for the test statistic, degrees of freedom, and then in the notes you can also see the formulas for the confidence intervals on the right under each of these cases. So I know these are intimidating formulas, but we can use Excel, we can calculate these things, and again, this is a situation where if we have the raw data and not just summary statistics, we want to use that data analysis tool, especially now that we have these big calculations. If we can use data analysis, we want to. And so in these situations, we'll choose the t-test option, the t-test to sample, and depending on if we're assuming our variances are equal or not equal, we'll either choose equal variances or unequal variances after that. So let's take a look at this next exercise. This says the airline industry measures fuel efficiency by calculating how many miles one seat can travel, whether occupied or not, on 1 gallon of jet fuel. And the data in the Excel file below shows the fuel economy in miles per seat for 15 randomly selected flights on Delta and US Airways. So here are two kind of populations, are Delta and US Airways. And it says perform a hypothesis test using alpha being 0.05 to determine if the average fuel efficiency differs between the two airlines. And it tells us to assume that the population variances for the fuel efficiency for these two airlines are not equal. So that automatically tells us that we're in this situation where we're doing a case one problem. We're assuming our population variances are not equal. And so we're using these formulas for case one. But this gives us the data. It gives us the sample data. So that means if we can use the data analysis tool, we want to be able to do that. So let's try to figure out what our hypothesis test would be. So let's see, we want to figure out our hypothesis statements, so our null and our alternative, and we want to say something about the average fuel efficiency and how that compares between the two airlines. So I should decide what's population 1 and what's population 2, and we get to choose here. We can choose whatever we want for population 1 and 2. Let's go ahead and choose Delta to be population 1 and US Airways to be population 2. And we want to see if the average fuel efficiencies, if we have enough evidence to say that those are different. We want to see if they differ. And so if we rewrite these in terms of the difference between the means, we would have that the difference in means is 0 for our null, and the difference in means is not 0 would be our alternative hypothesis. And so let's open up the Excel file and take a look at this sample data here. So here's our sample data, and we said that Delta was population 1 and US Airways was population 2. And the problem said to have our alpha be 0.05, and we're testing to see if the difference in means is 0 or not 0. And so we were assuming that our variances, our population variances, are not equal. That's what the problem said to assume, and we want to test this hypothesis that we wrote out. So since we have the data, let's go to this data analysis tool. And we want the t-test to sample assuming unequal variances. It's a t-test because they didn't tell us the population standard deviations. We only have information about the sample, and they told us that we're doing this situation where we have unequal variances. So if I hit OK, my variable 1 is going to be this delta data. So I'm going to highlight the delta data, and I included the delta label in what I highlighted. And then variable 2, I'll select B2 to B17. And my hypothesized mean difference was that difference in the null hypothesis. So I was testing to see, in my null, I had that the difference in means was equal to 0. So that number on the right-hand side goes in that hypothesized mean difference. And then my alpha is 0.05. And let's put the output right here. So let's take a look at what this is showing us. Okay, so we have all of this information here. This thing labeled t-stat is our test statistic. And let's see, our hypotheses, I don't have them typed in here, but they were that the difference in means is equal to 0 and the alternative was not equals to 0. And so that's a two-tailed test, which means I'm interested in these two-tail values here. So let's see, this t-stat is the test statistic, and then this p of two-tail, that's the p-value for this two-tailed test, and then this next value says t critical two-tail. This is the positive critical value. Because it's a two-tailed test, we have two critical values. The other critical value would be the negative version of this. So the only one we really have to look at is our p-value, and we want to compare that to our alpha. So our alpha is 0.05, and this p-value is less than our alpha. So that probability is smaller than our cutoff. So that means that we would reject the null. The other way we could look at this is say, okay, our critical values are 2.06-ish and minus 2.06, and our test statistic is to the left of the smaller test statistic, and so it is in the rejection region. So here we would say there is sufficient evidence from our samples to conclude that the fuel efficiencies for Delta and US Airways are different, because I rejected the null, and the null was that they were equal, and I have enough evidence to conclude that the alternative is true, which is that those averages are different. So I should say that the average fuel efficiencies are different. And so we had to be able to interpret this output. We had to know what kind of test to do, to know what tool, what test in Excel we should be doing, and we had to be able to interpret the output from it. But this meant we didn't have to do any of those big calculations that we saw in the notes, which is really nice. And so it's really nice when we have the data and we can use the data analysis tool in Excel.